the mutex is at an offset 0x28. Okay, so we take the address of that structure, which is 6BE40, we add 28, we figure out what is the contents of that particular data location. So if you look at the stack, you see that the mutex vector enter is a call in the kernel saying that, okay, I want to acquire this mutex, but the mutex is currently owned by somebody else, so I need to go block myself. So in order to block myself, I have got to call turnstile block, which is another function in the kernel. And the turnstile block requires to take the dispatcher block of the thread which is the owner of the current of the mutex. So we find that the owner of the mutex is basically this structure 30340, the one ending at the end. And then we see what that guy's E underscore P points to. That points to that 0x feed face on which we actually trap. So something is wrong here. And the lock pointer of that particular thread structure cannot be that nonsensical value. So let's go back and look at the buffer from which we obtained the mutex on it. So notice there are two values which are highlighted at the dump of that buffer. So if we XOR the two values, we find that the pattern is ALLOCATD, which actually indicates that actually the buffer is allocated. So we figure out who allocated that buffer. So again, we are using a lot of features from the kernel memory allocator. This particular crash file was taken with kernel flags enabled. So we do a boxctl audit to find out who actually allocated the buffer. So the buffer was allocated by, I guess some people might have been discussing, by a thread, by our panic thread only. You have thread ID, and following the thread value is the cache value. So this is telling us from which particular kernel memory cache this particular buffer came from. So the buffer came from a cache which allocated only 32-byte buffers. But if you look at the access of that buffer, we were accessing the 40th member of that particular buffer. So clearly we have oversized, we have access to a field which is much beyond what we actually allocated for. So this turned out to be a case wherein the customer had an older version of the CPC driver and a newer kernel. And this caused a mismatch in the structure, and this resulted in a panic. Okay, so here actually nobody is at fault except the fact that okay, you mixed and matched two different versions of software, and that resulted in a behavior which is totally undesirable. So the bug was okay, there's no bug, you just upgrade the driver to the latest version and the problem is solved. Okay, so going on to live debugging. Till now we saw postmortem debug, so we have a crash file, we need to figure out what has happened. Live debugging is that way better in the sense we have a lot better tools. And when is it useful? It's useful when, let's say, the system is hanging and the system is coming up. Or it's like way early in the boot process wherein the dump device is not configured, so you really can't take a crash file. So again, what are the tools that we have available? We have the kernel debugger KMDB, so you can boot in KMDB, set breakpoints. So there are various ways to set breakpoints, disable them, enable them, watch values in the kernel. Then you also have a lot of p-tools, pstack, ps, pflags, stuff like that. All these are extremely useful when you are using live debugging. And of course, truss and the numerous options it has that people can spend good amount of time reading the transcript and still not figure out how to use truss for it. Okay, so Brendan Gregg is going to give a presentation on weak case 2 days from now, so I'm not going to spend much time about it except say that ever since this tool has come into existence, I think how my job and a lot of support engineer job has become much easier because we can now ask questions, get real-time answers from the systems as such, and figure out where the problem could be. So the things which we find useful are the fact that you can trace every kernel function entry and return. So you can put probes wherever you want, also the kernel. And okay, lots of times the stacks which are leading to those kernel functions itself is a big eye-opener. So you wouldn't have thought, okay, this code could have got called in this way. So that itself is a big deal, lot of times. And okay, a brief introduction, dtrace gives you the D language, which allows you to write various actions, and you can predicate on certain variables being true and stuff like that. It gives you a lot of powerful data management primitives like aggregations and quantization. You have multiple providers. You have providers for every important kernel subsystem, like the scheduler, the proc, the I/O. So you can ask things. You can get information like, okay, which thread was on CPU, whom did it give the CPU to when it did the context switch to. For what reason is it blocking? What is the stack which leads to that particular thread blocking? Every system call is a probe point, so you can figure out what system calls are being done throughout the system, which system calls are failing throughout the system, something which Trust cannot do because Trust works on a particular process. So here you can work on a systemic basis and figure out, okay, what are the things which are failing on the system. You have various different consumers. The most common one is dtrace. Logstat has been rewritten to be a dtrace consumer. You can get interrupt statistics, what interrupts are coming on what CPUs. Then of course you have anonymous tracing, so you enable some descripts on the system, and then you know that the system would panic. So you want the state of the system leading to the panic, so which is when you use anonymous tracing. Or when the system is booting up and you don't have any terminal associated, so that time you use anonymous tracing and you log all the trace information in kernel buffers, and then you have mdbd commands to extract those information. Okay, so we'll just skip towards kernel deadlocks. So what are deadlocks? You have a set of processes, each one waiting for one another. So they form a cycle, and as a result, along these processes are threads which are involved in the cycle make any forward progress. So eventually the system gets stuck behind some of these threads, and the system basically hangs up. So the most common deadlocks are the ones which are involving condition variables of semaphores. So you have two threads, each one waiting for on some condition variable which would probably be signaled by the other thread. So you have two threads, three thread, four thread, four-way deadlocks. Then you have deadlocks due to memory. Basically, resource crunch, physical memory exhaustion, or your counting semaphore is undersized. So you said my counting semaphore I have initialized it to 15. That means I can maximum lose 15 sema-Ps, and then hopefully one of those guys will do a sema-V, and then the system would progress. But then that 15 turned out to be very small because for whatever reason. So you need to end up increasing that, or maybe use some other synchronization primitive to overcome those problems. Then you have other miscellaneous deadlocks which are like between the file system and the virtual memory interaction. You have certain deadlocks. So this thread took a particular mutex or a redirect enter, did some various activities, and comes back and wants to take the same mutex redirect enter lock. So it's basically wanting to take a lock which it itself has to release before the system it can make forward progress. So how are deadlocks detected? People with the OS background would remember about Banker's algorithm, when you figure out whether allocating a particular resource to this thread would lead to an unsafe situation or something like that. But it turns out that Banker's algorithm cannot be implemented in practice because you wouldn't know beforehand what this thread is going to look for in the future, and what are the locks it might require in the future. So Solaris does not implement the Banker's algorithm, neither do any other OS as I know. But we could detect deadlocks whenever mutex access or a redirect lock access is being made. Not access, the request to take that mutex or the redirect lock is being made. So in OpenSolaris, what do? We can detect deadlocks which involve the mutexes and the read-write locks, and we just decide to panic because we detect that this is going to cause a deadlock. So the best thing is to basically take the system down because otherwise anyway it would hang up or it would cause other catastrophic failures. So earlier you detect, you just go ahead and panic the box. The next one is how do we detect deadlocks in OpenSolaris, as in what do we do? So recall about priority inheritance. So you want T1 is waiting for a synchronization object which is held by T2, which is waiting for a synchronization object which is held by T3. And their priorities are 10, 30, 20, 10. So T1 needs to will its priority to T2, figure out what T2 is waiting for, try to will its priority to the guy who's blocking T2. So since anyway we are blocking this chain of owners, we can actually figure out that, okay, are we trying to build the priority back to ourselves at some point? So do we detect a cycle? If we detect a cycle, we know that it's a deadlock and we decide to panic. So that code is extremely neat, which tries to detect this deadlock. So I'll just put a URL to that particular source code location. Going forward, so this is the example of a deadlock wherein the system detected that this would cause us a deadlock, so it's a cycle in blocking chain and it panics. Right. So going forward, how do you analyze and figure deadlocks? You basically look at the crash file, figure out the threads which are involved in causing the deadlock. So the key question is to figure out who holds what mutexes or what deadlocks and wants what. That way you discover the deadlock, and then once you know the deadlock has happened, you then figure out how to trigger the deadlock by writing simple scripts or simple C programs. In some cases, a couple of while loops are good enough to trigger the deadlock, but in some cases you might need to write a small device driver to exercise a particular kernel code fragment repeatedly. So these are the examples of various deadlocks. So here there is a deadlock between the file system and the virtual memory. So the thread on the left, thread 1 is trying to do a direct I/O read. So direct I/O is basically a mechanism where you can read from the file on the device into your application buffer without involving the kernel caching. So there's a component called segmap which does not get involved when you do this direct I/O read. So in this case, the thread on the left is actually trying to do a direct I/O read. It figures out that actually the file is there in the cache, so it needs to invalidate the cache. So to invalidate the cache, it needs to take the page locks on each of the pages of that file which is there in memory. So while trying to take that page locks of all the pages in the memory belonging to that file, it blocks on one of the pages, which happens to be, that page lock happens to be held by thread 2. And thread 2 holds that particular page lock and wants the read-write lock of the file which thread 1 is owning. So as a result, thread 1 is waiting for thread 2 and thread 2 is waiting for thread 1. And such a deadlock is not detected automatically by Solaris. Eventually, some other thread 3 would come and wait on thread 2, thread 4 would come and wait on thread 1, so on and so forth, and eventually the system would hang up. And at that point, would take a crash file. And then, based on looking at the crash file, you would detect that these two threads are involved in. Okay, so this is another interesting deadlock involving autofs and devfs. In fact, this was hit maybe a couple of months by a couple of customers. So it turns out that most people don't have a /misc in their root file system, right? Nobody would generally create, but this customer had created a /misc in his root file system, and on top of it, he had made /misc to autofs mount point. And when he had that, with such a configuration, at some point, there was a process which was doing find/devices sudo on the system, and you had automount d which is trying to open /dev/udp, which actually points to /devices/sudo, one of the modules there. So automount d is waiting for a read-write lock which is held by the find thread. The find thread is trying to do a mod load of a particular kernel module, And so the find thread T2 is triggered T3 to actually load the module. And T3 is a system thread which is in the process of trying to read /disk/sparmina in RSM ops, which is the kernel module which it wants to load. And it tries to contact the autofs daemon. So since the autofs daemon is stuck, you have T1 waiting for T2, T2 waiting for T3, and T3 waiting for T1. So it's a three-way deadlock. So the workaround here was simple, basically. Don't make /disk your mount, your autofs mount point. Right? So these are deadlocks which probably you wouldn't figure out from the source code at all. It's only triggered on a particular customer system with his unique configuration. Anyway, we did fix this in Solaris, so you can still have /disk as your autofs mount point if you get to. Okay, so this is another deadlock which is involving the kernel Cageout, just running out of time. This was a deadlock seen on OpenSolaris systems when trying to boot guest OpenSolaris 2009-06 as a guest on a Xen system. Again, a three-way deadlock, T1 waiting for T2, T2 waiting for T3, and T3 waiting for T1. So how do you solve deadlocks? In most cases, you can define the lock order and say, look, this is the order in which these locks have to be taken. But a lot of times it turns out that you actually can't enforce that rule of lock ordering. You might still need to have cases wherein you need to take the locks in a reverse order. So in which case you are liable to be vulnerable for these deadlock problems. So one way to solve them is instead of doing a blocking call, you do a try enter. Okay, can I try for this mutex, and if it is free, you get ownership of that mutex or the read-write block. Otherwise, you release whatever locks you are holding and try the blocking sequence again. But this can lead to live locks wherein a couple of CPUs are busy doing the same thing, each one expecting the other to release, and so you just change the problem from a deadlock to a live lock when instead of everything hanging, everything running, but no progress being made on the system. So, okay, what are race conditions? Races are basically two threads trying to access the same memory. This one is writing, the other is reading. The outcome of the race is dependent on the sequence of access to the memory locations. Again, races can be catastrophic, they can cause system hangs, panics. Sometimes can lead to data corruption. We had a race in the UFS code which led to data corruption. They're extremely hard to reproduce. They occur under extreme load conditions, typically seen only on customer systems, very hard to reproduce on our labs. But once you know what the race is, then you have figured out the code fragments, again you exercise some test code to pound hard on the code fragments in question and then shake out these bugs. The key point with races is the interleaved execution of the thread. So programmers really think that, okay, this is the sequence of operations, this is the sequence of operations. They forget about the fact that the sequence of operations can be happening in parallel on multi-CPU machines. And the order and the interleaving of these sequences of executions generally trigger these races. So again, you need to have good analytical skills to figure out the races.
Sorry, I really do.
Okay.
Thank you very much. One thing that I'm not sure whether you've got it on your references page is all the source for all this low-level stuff about scheduling is actually available on OpenSolaris.org for at least OpenSolaris and Kernel.org for Linux and FreeBSD.org, etc., etc. So if you are at all interested in this and or you think you've come across an instance of something like this, go and look at the source and ask lots of questions. Right. So we're going to have a break for lunch. Lunch is just outside where morning tea was. We have a little bit of a sort of a demo room with some